A lot of times when we are working with constrained optimization problems, we don't have the functions to begin with. We actually have to solve a problem and we're subject to some sort of constraint. So let's look at one of the classic examples which deals with optimizing the volume of a box. So maybe you work for Amazon and the goal is to figure out a box that could contain the most volume in it, but that uses the smallest amount of material. So a box designer wants to construct a closable box as shown in this figure. The designer requires that the sum of the height and width of the pieces of cardboard used to make the box be 120 inches. What are the dimensions of the box with the maximum volume? Okay, so we see that this is a constrained optimization problem for two reasons. One, we want to find maximum volume. Okay, so there's our objective. What do we want to do? We want to maximize volume. But if we wanted to maximize volume, we could just get the biggest sheet of cardboard we could possibly find and fold it up and make the biggest box that we can think of. But there's a constraint. And the constraint says that the sum of the height and width of the piece of cardboard used to make the box be 120 inches. So there's our constraint. That's limiting what we're allowed to do. And a constraint is just that. It limits what we are allowed to do. So we want to maximize, I'm going to write this out just in words, maximize volume subject to the sum of height and width of cardboard is 120 inches. Okay, so we have to do two things. We have to figure out what this volume function is, and we also have to write a function for the sum of the height and the width of the box to be 120 inches. Well, we see that we have three variables. We have h, we have w, and we have l. So w is the width, l is the length. Let's think about why we're using 2h here. Why not just call it h? Well, if we look at the box kind of unfolded in its most raw form, this is the shape of it. And it actually turns out that these flaps right here, these top and bottom flaps, are all going to have a width of h. Okay, so for example, that right there is going to be h units. So basically what we're saying is that the box will be twice as high as the width of one of those flaps. All right, and then we also see that the way this portion here is going to be 1/4 of the width. So let's think about how this might evolve. So first of all, these are going to be the sides. So this side here corresponds to this side here. Then we can think about this being side 2, right? Side 1 and side 2 have to be next to each other. So that means side 2 is going to be one of those two ends. And we also see that that's going to be a length of L, which is this piece here. Side 3 is going to be the back, side 3, and that's going to be W units long, W units wide. And then side 4 is going to be this side here, but we also have this little flap. And we have that flap just in order to probably connect the ends of the box, right? So if you imagine this getting glued to side 1, right? This side right here is this side, and then we're going to have this flap to basically join side 1 to side 4. All right, so the volume of a box, of a rectangular prism, is going to be length times width. That will give us the area of the base, length times width, but then we need to multiply it by the height to get volume. And well, let's plug in some variables here. Let's call our volume function, we'll call that V of L W, and H. We have three variables in there. So that's going to equal, the length of the box is simply L. The width of the box is W. And then the height of the box is going to be 2H. 2H. This flap doesn't really come into play with the volume. The flap is basically going to have dimensions that are going to be quarter of the width and 2H tall. So it's not actually going to contribute to the volume. It's really just going to, if anything, that small thickness of cardboard will remove some of the volume. But that's pretty negligible, so we're not going to worry about that. It's a non-practical implication. So there's our objective function. Now you see that it involves three input variables, L, W, and H. So when we build our Lagrange multiplier method, we're actually going to have three partial derivatives. We're going to have v with respect to L, v with respect to W, and v with respect to H. But before we go on to that, we have to ensure that the sum of the height and width of cardboard is 120 inches. So what we want to do is we want to maximize the volume subject to the sum of height and width of the cardboard is 120 inches. Well, what's the height of the cardboard? Well, the height is this entire thing. That's the height of the piece of cardboard. And the width of it, or you could switch these. This is not going to be important because we're going to be adding them together. So if you happen to call this width and call this height, I mean, that's completely up to the observer. And then the width is this entire thing here of the piece of cardboard. Okay, so let's think about this. The sum of the height and the width. Well, what is the height? Well, the height is h plus 2h plus h. That's the entire length. We have this piece plus this piece plus this piece. That's going to give us the entire height. Well, h plus 2h plus h is going to be 4h. And w plus L plus W plus L plus a quarter W, well, that leaves me with two L's. It leaves me with two W's plus a quarter W more. So 1W plus 1W plus a quarter W is 2 1/4 W, or we could write 2.25 W. All right, so this here is our total height of the sheet of cardboard. This here is the total width of the sheet of cardboard. And we want that to be 120 inches. Great, so now we have our optimization problem built. That's this entire thing here, and now we can work on solving it. So you can see that this took us some effort to actually get to the point where we could even carry out the analysis. First, we had to build the model, and now we're going to solve the model. So what we need to do is, in our first set of equations, we need to ensure that the partial derivatives of our objective function. Now, our objective function here is actually called v. I'm going to go ahead and refer to this as f of L, W, and H. So we're going to need f sub L of L, W, and H. We're going to need f sub W of L, W, and H. And we're going to need f sub H of L, W, and H. Okay, so this is the same process. This is building our system of equations that we're going to need to solve is equal to lambda, the Lagrange multiplier, times the same partials, but of G. Now, by the way, if you had listed the variables in different orders, if you had done W and then L and then H, it's just important that you do the same thing over here, W, then L, then H. So by going L, W, and H, there's no particular order that needs to be accomplished there. Now, this right here is our G, and in this case, G depends on L, W, and H. H. G is just the generic name that we give our constraint function. So then we're going to need G sub L of L, W, and H. So as long as we do L, W, and H here, we have to do L, W, and H here in the same order. Then we're going to have G sub W of L, W, and H, and G sub H of L, W, and H. So if you have 3 input variables, you have to have 3 partial derivatives. If you have 10 input variables, you'll have to have 10 partial derivatives. And then our final constraint is that 4H plus 2L plus 2.25W has to equal 120. Okay, so we'll first move to use technology to help us find the partial derivatives of f and of g. Here in Wolfram Alpha, I have d slash dl of our volume function, L times W times 2H, gives us 2HW. So we would want to write that down. And then we want to do ddW of L times W times 2H, which is 2HL, and ddH of L times W times 2H, which is 2LW. Okay, so here I've just listed f sub L, f sub W, and f sub H. Those are our 3 functions there. Each of those is going to equal lambda times the respective partial derivative of g. So I'm going to write this into 4 separate equations. And so we'll have lambda times whatever the partial of our constraint function is with respect to L, and with respect to W, and with respect to H. So now we're going to take the partial derivatives of this guy. Now this is pretty straightforward to take the partial derivative of, but again, you can take this, dump this into Wolfram Alpha and type in ddl, ddl, ddw of this, and ddh of this. And what you'll get is, well, the partial derivative with respect to L is going to be 2. The partial derivative with respect to W is going to be 2.25. And the partial derivative with respect to H will be 4. So now we have our system of equations. This system of equations is the system that we need to solve. So notice that we have 4 variables and we need 4 equations. 4 variables, 4 equations. And this is going to be true. If we have 10 variables, we'll have 10 equations. 9 of those equations would come from the 9 partial derivatives, if there were, again, that many variables. And then the 10th equation is going to be would be the constraint function. So next we need to plug this system into technology and have it solve for W, L, W, and H. Here we have our output. Now I just want to emphasize that it's best to put multiplication signs as often as possible. If you omit them sometimes, technology may not understand WH as W times H. So having explicit multiplication signs is really useful. 2 times W times H equals 2 times capital L. Now, capital L is what we're using to denote the symbol lambda. And so we just have to distinguish between the lowercase l, which is our actual length, and capital L, which is what we're using for lambda. So be cautious if you are using a lowercase l, do not use lowercase l to represent lambda. You could use some other letter to represent lambda. Just make sure that when you're inputting it in here that you know which of the variables is which. So the output that we get is down here, and it looks like there's more than one solution. At first, it might seem kind of confusing which of these solutions we should pick, but if we look at them more carefully, the first solution says, and by the way, if you click on exact form versus approximate form, we probably want approximate form just so that we know how many inches the box is. And this first solution doesn't really make a whole lot of sense because it's saying that if h equals 0, well, that's a box that has 0 height and 0 length. So that doesn't make sense in the context of the problem. The second solution, h equals 0, L equals 60, doesn't make sense either, again, because the height is 0. The third solution says the height should be, h should be 10, L should be 20, and W should be 17.8. That's lambda. We're ignoring lambda for all intents and purposes. The bottom solution also doesn't make sense because that has a length and a width of 0. So our optimal solution is going to be h equals 10, L equals 20, W is about 17.8. So we have scratched out these three solutions here, and we're concluding that h equals 10, L equals 20, and W is about 17.78. Now, that's not where we have to stop the problem. We have to think about what the question was. The question is, what are the dimensions of the box with the maximum volume? Well, that's going to be this dimension here by this dimension by this dimension. So remember, the height of our box is actually 2 times the value of h. And so our box will be 2h by L by W. And I guess oftentimes we list length times width by height. So let's go ahead and do that. Length by width by the height, again, which is 2h. The length is 20. The width is 17.78. And twice the height is going to be by 20. And that's how those should be the dimensions of the box. The units are all in inches. So this is going to be 20 inches by 17.78 inches by 20 inches. And we want to maximize the volume. It doesn't ask us what the volume would be, what the maximum volume would be, but let's go ahead and figure that out anyway. We know that the volume as a function of these three is going to equal our objective function, which is L times W times 2h. L times W times 2h. So the volume with a length of 20 inches, a width of 17.78 inches, and the h value being 10 is going to be 20 times 17.78 times 2 times h, which is 2 times 10. And we can plug that into our calculator. 20 times 17.78 times 20 comes out to 7,112. Okay, and that's going to be, it's inches times inches times inches, which will give us inches cubed, or 7,112 cubic inches is the maximum volume. Now, at this point, we would want to, again, ensure that this is a maximum. It's a little bit trickier to confirm maximum values when you have 3 input variables. But one way to do this would be to pick a couple of values of L, one that's smaller than 20, one that's bigger than 20, and also to pick a width that is smaller than 17.78 and bigger than 17.78. So you would really want to look at 4 points here surrounding our critical point. But we're not going to get into that here with 3 variables. We're only going to work on that with 2 variables.